we're going to be doing today is the notes on Vesper. Everybody say Vesper. Vesper. Now, it doesn't look like Vesper, it looks like VSEPR, but any of the scientists will know this to be Vesper. So what V word have we been talking about? What are valence? Perfect. So the first word is valence, and not energy levels, but they also may call them, starts with an SH, they also call them shells. So valence shell is the first V and S. And then we're talking about what are in these valence shells. They're called electrons, and they come in twos, which we call electron pairs. Good. So the next two words are electron pair, and then the R word. What do you know that negatives do to each other? They don't attract, but they repel. So it's called the valence shell electron pair repulsion, and this is a theory about it. Okay? So I want you to circle the V, the S, the E, the P, and the R. So it's Vesper. Now you do need to have this memorized, so this does need to be memorized. So we're going to do this together, and we'll do it 5 times. So here we go, and we'll pause the video so that we can get this. Everybody say valence shell, electron pair, repulsion theory. And the theory basically provides us a way of determining the architecture or the geometry of a molecule. So before we do this, I do want you to know that this Vesper model is specifically for covalent molecules. But we know that in addition to covalents, we also have ionics. Now I do have ionics listed here, but really the ionics don't take on these shapes. The ionics only form what we call crystals. And the crystal structure, if you draw a box, and then a box in the middle of that, so you do a cube, basically what happens is, I'm going to switch my color here, you get alternating positives and negatives. So you may have a positive here, but then it would be a negative right next to it, and a negative right next to the other positive, and then a positive there, and a negative, positive, negative, positive, negative, alternating, so that every positive has negatives surrounding it, and every negative has positives surrounding it. So this Vesper model predicts the way that electron pairs around an atom will be what as possible? Well, if they're repelling each other, then are they going to be really close or really far? Really far. So these are as far apart as possible. And I want you to know this for a multiple choice question on your test. And the question may ask you something along the lines of, which of the following correctly describes the Vesper model, okay? Or is an idea of the Vesper model. And a choice may be something like, the electrons will be as close to the nucleus as possible. Well, that's not what the Vesper model says, okay? Vesper model is talking about what being as far apart as possible. The electrons are going to be as far apart as they possibly can get, okay? So that's what the model is basically saying. Therefore, the shape of a molecule is simply determined by the repulsive interactions between what types of particles? Only the electrons. Awesome. Between the electrons. So these tiny, 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 tiny little electrons, they are what determine what your shape of your molecule is going to look like. All right, 2 major steps here. The first one is we're going to draw a Lewis dot diagram where we're going to use the duet and the octet rules, which means 2 and 8 electrons. There are some exceptions, so we will talk a little bit about those exceptions again today. And then what you're going to do is you're going to use this chart in order to match what type of molecule, what type of shape the molecule has, okay? So there are more shapes than this, but in AP you'll learn more. At this level, we're just going to do these major ones. And they can be organized very differently depending on who's teaching it or what book you're looking at. So my way may be a little bit different from someone else's. The way that I do this is I put the total number of atoms over on this side. And so we have 2 atoms, and if you have 2 atoms, we're just going to have a linear shape. You can have 3 atoms where this is in a line, so we call that linear, or it can be what is called bent. You can also have 4 atoms where you have 1 in the middle and 3 going around. We're going to either call that a planar equilateral triangle. So you can see that we could make an equilateral triangle going along the edges of it, or they'll call it trigonal planar. You can also have what is called a pyramidal shape. Trigonal pyramidal or pyramidal. And that's where your central atom is at the top and then the 3 are under. You can have 5 atoms where you have 1 in the middle and 4 around. They call that a tetrahedral. 6, we're only going to have 1 choice. That's 1 in the middle and then 5 going around. and 7 atoms is 1 in the middle and 6 going around. We're going to call that octahedral. This is pretty easy to remember. Tri represents how many? 3. And bi typically represents 2. And 3 plus 2 is 5, and there's 3 plus 2, which gives us a total of 5. So that's easy. It's trigonal bipyramidal, okay? This one here, I don't like the name of it. Why do I not like the name? Because it's got 6, and 6 would actually be not octa, but 6 would be hexa. So they don't call it hexahedral. And there are what they call electron domains, and so that's why they call this octahedral. But it's still not too bad to remember, because some student years ago said, they said, Ms. Ismail, it's okay because if you connect this and make a figure 8, then you'll remember that it's octahedral. So they're like, it's okay, because if you just do an 8 like that, then you can call that octahedral. So just as a way to remember it, okay? But it really does have 6 going around the central atom. So let's come back up to the top here. If it's linear, then, and there's no central atom, we're going to draw O2, okay? And so O2, we're going to first figure out, is it ionic or is it covalent? Well, it's obviously what type of molecule. They're equal, so we call those nonpolars. So this is covalent, and we really don't care if it's polar or nonpolar at this point. We just want to know if it's ionic or covalent. And this one's covalent. So we're going to add up our valence electrons right under. And oxygen, we know, has how many valence electrons? You look at the Roman numeral above, and it has 6. So we're going to do 6 times 2, which gives us a total of 12 valence electrons. So we're going to put O dash O, and then we're going to start putting our dots around. So we've got 2 in the middle, 4, 6, 8, 10, 12. You cannot put any more dots on. So if I have 12, I can only put 12 dots around it. So what's wrong with it?
The other one doesn't have 8.
Perfect. This one doesn't have 8. One of yours doesn't have 8. Remember, they're really nice and friendly. They're going to share. So we're going to take 2 from here, and we're going to drop it in between. And now how many do both of them have? 8, and that's obeying the octet rule. To do the shape, all you have to do, you can leave all the dots out. You do have to show the double and the triple bonds, though. So you just do the shape that way, and you would call this linear, okay? And let's talk about whether the molecule is nonpolar or polar or ionic. It's obviously not ionic, okay? Is everything equal in this molecule? Yeah. Yes. So we're going to call this a nonpolar molecule, okay? This is called a nonpolar covalent molecule, where everything is being shared equally. Okay, so let's take a look at this simulation. So I'm going to remove everything, and if I have one single bond, no matter what, no matter how these atoms are positioned, no matter what, I can put a line in between them. So we call that what shape? Linear. So now what I'm going to do is I'm going to remove it, and I'm going to put a double bond in there. Same thing, just like O2, like we were just saying, it's still going to be linear in shape. Okay, so anytime that you have 2 atoms, it's just going to be linear in its shape. So let's try to see what happens when we draw CO2 or BEF2. Let's do CO2 since we won't do an ionic one yet. We'll do one ionic one later. Because the ionics don't really take on these shapes, they just do crystal structures. So CO2. All right, we need to check to see if it's ionic or covalent. We really just want to know if it's greater than 1.8, okay? Because then it's ionic. Carbon's 2.6 and oxygen is 3.4. So 2.6 to 3.6 would be 1. I know it's less, it's 0.8. So that makes it not ionic, but covalent. So I'm going to add up my valence electrons. Carbon has 4, and each oxygen has how many? 6. So 6 times 2 is 12, plus another 4 gives us 16. So we're going to put the C in the middle, and then we're going to put the O's with the dashes in between. Okay, go ahead and throw your dots around. So remember, the way that I do this is I start counting 2, 4. You have to do the outside atoms first and then do the central one. Okay, so 2, 4, 6, 8, 10. Then I'm going to come to the other oxygen. 12, 14, 16. Stop when you get 16. Okay, stop at 16. Is everybody okay? No. Who is not stable yet? The carbon. The carbon only has 4 electrons. What do you do? Double bond. Double bond. Awesome. If I take 2 from here and I put them in between there, now this oxygen still has 8, but carbon only has 6. So what do I need to do again? Another double bond. Now a triple bond would work, that does obey the octet rule, but this one is the more stable of them because we said that math word, it has what? Symmetry. Awesome, it has symmetry, very good. So this is the one that we would prefer to draw. But the triple bond and a single bond on the other side does also work. All right, the shape of it. The electrons are going to separate themselves as far apart as possible. And as far apart as possible, there are no dots in the central atom, is exactly what it is. So you're just going to do C double bond O without any dots. And we're going to also call this linear. Okay? Now, there are no dots on the central atom. There are two things that are going to indicate whether or not this is a polar or nonpolar molecule. Okay? We know that the bonds are polar because we have an electronegativity difference. If we take a look at this chart for a second, so let's take a break to take a look at this chart here. We've got 2.6 and 3.4, so we said our difference is 0.8, okay? What you do is, you come down to this chart here, and if your electronegativity difference is 0, then it's nonpolar, and it's automatically a nonpolar molecule. If it's greater than 1.8, it's ionic, and it's automatically an ionic molecule, quote unquote. It's a formula unit, but ionic molecule. The only one that's in question is when you calculate and you get a difference that's greater than 0 and less than 1.8. We're going to call that polar. And if it's polar, to figure out, those are polar bonds. To figure out what type of molecule you have, check the central atom. If you have dots on the central atom, it makes it polar. If you don't have dots on the central atom, check the outside of it. It's a pizza roll. Does everything look the same going around it? And if everything looks the same, then we're going to call that equal. And equal is what word? Nonpolar. Okay? So we had a difference of 0.8 on that one. And so if we had a difference of 0.8, we know that in that case, we said that the oxygen has a higher electronegativity value. They actually draw what's called a dipole moment. And they draw it out toward the oxygen, and from the carbon out toward this oxygen with the value of 0.8. Okay? That's called the dipole moment. So we know it's pulling in opposite directions, but it's pulling equally in opposite directions. Are there dots on the central atom? No. So we have to use our pizza rule. Do these oxygens look exactly the same to you? Does it look like a mirror image to you? Yeah. So guess what we call this? Non-polar. It's a non-polar molecule. Polar bonds, but it's a non-polar molecule. All right, let's try the next one. Let's do H2S, because we've already done H2O, so let's do H2S. So again, first step is it covalent or is it ionic? So we just want to make sure it's not greater than 1.8. H is a 2.1, and S is a 2.6. So that's only a difference of 0.5. Okay, so we know that this one's going to be covalent. Let's add up our valence electrons. Hydrogen has 1, but times 2. And sulfur has 6, so we get a total of 8. Which one goes in the middle? S. Good. So S goes in the middle, and then our H's go along the sides. What do you remember about H? No dots, and no double bonds, and it's done. Okay? H is obeying the duet rule right now, so it's all set. So where do the other 4 electrons go? On the sulfur, on the central atom. 2 there, and 2 there. But this is actually not the shape. So I'm going to give you an analogy, okay? Free electrons, I want you to think of as people being single, okay? And the bonded pairs of electrons, these bonded ones, where you have 2 that are connecting 2 atoms, we're going to call those the dating ones, okay? You know that your friends or people that you know that are dating, boyfriend, girlfriend, they can get really nice and close together. But if you are single, like these lone pairs of electrons are, you actually need your space. If someone comes up to you and starts snuggling with you, you're like, yo, I can smell your breath. I need you to step away. Okay? I'm single and I need my space. All right? The ones that are bonded are going to get really close to each other. And here's why. The ones that are bonded actually are attracted to each other. What is at the end of this? Well, this is a nucleus, and what do you know that the nucleus has inside of it? Positive protons. And so what ends up happening, let's go to our simulation, we've got 2 single bonds and 2 free electron pairs. So let's see what happens. Let's remove all. Oh, by the way, on the last one, I did want you to see this, where we had CO2 with 2 double bonds. It looks like this. And so if you look at the angle, it's a 180-degree angle, okay? It spaces itself out as far as possible. So now let's do the next one. Let's remove all. And let's do single bond single bond, and then let's do 2 lone pairs of electrons. All right. If you notice, what ends up happening, I want to see if I can see both of these together. What happens is it bends it, okay? These two can get close together because this is a positive nucleus and it's slightly attracted to the electrons here. And this is a positive nucleus and it's slightly attracted to those electrons. These are what we're calling the single or the free electron pairs, the non-bonding electron pairs. And these require more space. They're like, give me my space, I'm single, okay? These require more space and these two can get closer together. So we call this shape is either bent or we can call it angular, okay? So in this case here, we're going to draw a double arrow here. And what it looks like is S, H, H with no dots anymore. You don't have to show the dots on the shape. So let's talk about polarity. We know that these bonds are polar because we said that sulfur has a higher electronegativity. It's actually the opposite of what the carbon's going to look like. Both of these are going to go toward the sulfur. Okay, it's going to go up toward the sulfur, which means they don't cancel each other out. 2 up arrows actually equal 1 big up arrow, where 1 right and 1 left, if these two are both going in opposite directions, they actually cancel each other out. You don't have to worry about the dipole moments though. All you have to do is use my rules. Are there dots in the central atom?
Yeah.
Yes. What does that make it? Polar. Awesome. These are polar bonds, and it's a polar molecule. Okay? Unequal sharing going around your atom. Next one. So, boron and aluminum, Betty and Al. There's that song by Paul Simon, okay? So, boron and aluminum, there's something special about them. They do not double bond, and how many electrons? Remember how many electrons they're fine with? 6. They can actually be stable with 6 electrons around them, okay? We're going to do Bi3. So everybody do Bi3, okay? Boron triiodide. So first thing is, let's find out if it's ionic or covalent. So is it greater than 1.8? Boron is 2.0 and iodine is 2.7. So 2 to 2.7 gives us what difference? 0.7, so we know it's covalent. So we're going to do this one as covalent. Let's add it up. Boron has 3 and each iodine has 7. So we've got 21 plus 3, which gives us 24 valence electrons. So the B is going to go in the middle, and then I'm going to do dash I, and dash I. And so now go ahead and start putting your dots around. So I've got 2, 4, 6. Stop when you get to 24, okay? Stop at 24. 8, 10, 12, 14, 16, 18, 20, 22, 24. Are the I's all obeying the octet rule?
Yeah.
Yes. The outside atoms all have 8. What about boron? It only has 6, but it's fine. Awesome. This is an exception. It's going to stay that way for the shape. The shape is that it's going to spread itself out. The electrons are going to spread themselves out as far apart as possible. This is not as far apart as possible because you have all this space up here, okay? So what they're going to do is your B is going to go in the middle of all 3 of them, and then you're going to put an I, a bond with an I on top, and then 2 I's at the diagonal corners in order to make what you see in your head as this planar equilateral triangle, okay? And again, it's fine that way. There are other molecules that will have a double bond in here that the central atom does need 8. You would have a double bond in the middle. So let's see what this looks like. Right, so we're going to do 3 single bonds. Let me remove all. 1, 2, 3 single bonds. And this is the shape that it has. And you can see that our angles are all 120 degrees. So we call this, everybody say it, planar equilateral triangle. Planar equilateral triangle. Okay? So that's our planar equilateral triangle. Next one. If you have 4 atoms, there's another option for your shape. So you can either have a planar equilateral triangle or it can be trigonal pyramidal. Watch when this happens. Let's do PCl3. Okay? So step number 1 is we need to figure out is it ionic or covalent. So we've got P at a value of 2.2 and Cl at 3.2. That's easy. What's the difference? 1. So that makes it again covalent. All right? So we're going to add it up. Phosphorus has 5 and each chlorine has 7. So 21 plus 5 gives us a total of 26 electrons. Same thing, put your P in the middle, Cl, Cl, and Cl, and go for it. Start putting your dots around. So we've got 2, 4, 6. Stop when you get to 26. 8, 10, 12, 14, 16, 18, 20, 22, 24. Where do the last 2 dots go? On top of the P. Awesome. Someone last hour said, can't you double bond it? If I did, I'll erase it after. So if I did, instead, if I put a double bond in there, what's wrong with that? That chlorine will have 10, okay? If you double bond instead, one of your chlorines will have 10. So you do not want to do it that way. Instead, you want your 2 dots just on top of the P so that everyone has 8 going around. Is everybody obeying the octet rule? We're good. What did we say about this lone pair of electrons that it's not paired? It needs more space. Guess what it's going to do to these 3? Put them closer together. So what this is going to look like is you're going to put the P at the top of the pyramid. Your central atom goes at the top of the pyramid, not at the middle like it was in the equilateral triangle. And then you're going to go Cl, Cl, and Cl. Okay, so let's take a look at the simulation to see what that looks like. So we still have 3 bonds, but in addition, we have 1 lone pair of electrons on the central atom. Kind of looks a little bit like, yeah, like a space shuttle. So we've got our 3 bonds that are closer together, and then we have our 1 lone pair of electrons. That's the free one, the single one. That's like you got to step back a little bit, you're too close. So that's the one that needs more space. Okay? Let's talk about if there's equal spacing or unequal spacing now of your electrons going around. Are there dots in the central atom? Yeah. Yes. And if there are dots in the central atom, what does that make this molecule? Polar. We didn't do this one. Let's come back up. Does everything look equal going around your central atom? Yeah. Yes. On this one then, we don't call that polar. We call that non-polar. Awesome. Okay. The last 3 are pretty fast. The only thing is I wanted to do 1 ionic one. So let's do GeF4 next. Okay? Germanium is a metalloid, so I do have to do the calculation for it. So Ge is 2.0 and fluorine is 4.0. What's the difference? 2. So I know that it's ionic. And we did ionics in 2 steps. Step 1 was write your charges. And then step 2 was put all 8 dots where? On the non-metal only. So let's put Ge in the metal. Do not do a dash. No dashes. Ionics do not get dashes. So we're going to go F, 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 and F. And now let's put our charges on. Germanium has a +4. So if you look above the symbol, it says +4. And what is each fluorine's charge? -1, -1, -1, -1. Where do all 8 dots go? On the F's. On every single one of them, you're going to put 8 dots, top, bottom, side, and side. Okay? So I'm going to go 2, 4, 6, 8, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8. Now, it looks like germanium is not obeying, well, in this case, it actually does look like it's obeying the octet rule. But a lot of times on the ionics, it doesn't. Keep in mind that if it looks empty, that means that the next level beneath it is actually full, okay? So if it looks like 0, that means the one under it is full. You do not do a shape for this. You're just going to say it's a crystal. Okay, it's a crystal structure. And what type of molecule would it be? Well, if it's ionic bonds, then it's what? Ionic. It's automatically ionic. Okay? So on the side over here, if you have a little bit of space, it's okay if you don't. I'm going to do CH4. So CH4 would simply look like this. Okay, it would look like that. Are there any dots around the central atom?
No.
No, and my H's are fine because they obey the octet rule, and carbon is fine. That would be what the shape looks like. So on this one, we would actually call this one non-polar because everything is equal going around it. But it is a polar bond again. Each one of these bonds is greater than 0 and less than 1.8. So this is what we would call the tetrahedral shape. Okay? That's what we would call the tetrahedral. All right, last 2. PCl5. We already did P and Cl, and so we said that it would be covalent. So this is going to be covalent again. So P has 5 and each Cl has 7, so 7 times 5 is 35 plus 5 gives us 40 total electrons. Put your P in the middle and now let's do our Cls. What do you know is wrong already?
It has 10 electrons.
It has 10. It's okay. Some of the atoms can accommodate more than 8 valence electrons, but it's only the central atom. So if there's an odd number, it goes to the central atom. If there's anything weird, it's the central atom. There's nothing you can do about this. It's PCl5, okay? So now we're going to put our dots on. 40, 2, 4, 6, 8, 10. So now you're just going to put 6 dots. Make sure around each one because we already have the 2. Put your dots on. Stop when you get to 40. And they're in pairs. Did it work?
Yeah.
Yes, perfect. Everybody else has 8, okay? As long as everybody else has 8, it's all set. When you go to draw the shape of this, you would just do the same thing, just without the dots. So everybody say trigonal bipyramidal. Trigonal, say it, trigonal bipyramidal. So it's tri and bi, 3 and 2. Okay, the last one. Oh, polar, non-polar. Does everything look equal going around the central atom?
Yeah.
Yes. So that would again be equal means non-polar. Yep. All right, and then the last one, SF6. So sulfur has a value of 2.6 and F is 4.0. So 2.6 to 3.6 gives us 1. So how many more? 1.4. So we got 1.4, which again makes it covalent. And we're going to add it up. 6 plus 6 times 7, so 42 plus 6 is giving us a total of 48. The S goes in the middle. F, 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 F. Again, are you obeying the octet rule on the central atom?
No.
No, it's accommodating 12, okay? And that does happen. Sulfur and phosphorus are kind of big on that. So now let's put our dots on. Count, again, you're starting with 12, and then you're going to count up to 48. And does this one work?
Yeah.
Yes, everybody has 8, again, except for the sulfur. And when you do the shape of this one, same thing. You're just going to put the S in the middle and then the F's all around. And that is what we are calling the octahedral. Everybody say octahedral.
Octahedral.
And this, does everything look the same around the central atom?
Yeah.
Yeah, so again, even though you have polar bonds, this is called a non-polar molecule. Okay, let me just show you what that looks like on here. So I'm just going to remove all, and I'm going to add 1, 2, 3, 4, 5. So there is, you know what, let me remove one of these so you can see tetrahedral. Here's the tetrahedral. It's kind of weird though because it's not really 1, 2, 3, 4 like we draw it. You can see that one's coming up in front, 2 are kind of going toward the back, and one's coming out. So it's spacing itself out equally, okay? And if I add 1 more, same thing. It's not just like 3 and 2. They're spacing themselves out equally, but when we draw it on paper, we're just gonna go 3 up and 2 down. And let's add 1 more to make it 6. And same thing on 6. So we're gonna do 3 ups and 3 downs, same thing. Okay, so we're just gonna do a couple of these problems together. What is a polar covalent bond? Polar means what again? What's the word? Unequal. This is unequal sharing of the electrons in a compound. And remember, what difference, electronegativity difference? It has to be between greater than 0, what did we say? Between 0.1 and 1.8. Perfect. 0.1 to 1.8 is going to give us polar, okay? And then you can fill in the rest of these. Let's do 2 of these together. BeCl2. So, beryllium. If you look at your periodic table, you will see that beryllium is a metal. So if it's a metal, then what type of compound is this? Ionic. So right here, I'm going to put a star and I'm going to write ionic. If it's ionic, you do not need to calculate it, okay? It's ionic, it's all set. Lewis dot diagram. We're going to put the Be in the middle. Remember, 2 steps. Cl, Cl, no dashes. What do we do instead? We do charges. Beryllium's a +2 and Cl's a -1. And where do all 8 dots go? On the nonmetal. So around each Cl. 2, 4, 6, 8. 2, 4, 6, 8. And we're done. What's the name of the shape? It really doesn't have a shape. We're just going to call it a crystal. Okay? We're going to call it a crystal. Normally you would have to sketch it, but it's the same as that. So we're done. And the molecule type. If it's ionic bonds, then what's your molecule type? It's also ionic. Perfect. Let's come down and let's do SBBr3 down at the bottom here. SBBr3. Okay. So the first thing is, let's check to see what our electronegativity difference is for our bond. So let me click over here. SB is 2.0 and BR is 3.0. So 2.0 to 3.0, what's our difference? 1. So I'm going to do 2.0 to 3.0, which equals 1.0. What does that make the bond type? Good. Polar covalent. Awesome. Polar covalent bonds. Lewis dot diagram. So now we're going to put SB in the middle and then BR, BR, BR. Well, we have to add up our valence electrons first. I'm just going to do it over here in this space. So SB, that's in the same group or family as nitrogen. So it has 5, plus each BR has 7, so 7 times 3. 21 plus 5 gives us 26. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Where do the last 2 go? On top of the SB. Perfect. So now let's fill in this box. What is the name of the shape? We need to look at our notes to figure this out. Which one has 3 single bonds and 1 lone pair on top? Look at this sheet. Which one matches that and has 3 singles and 1 lone pair? Trigonal pyramidal. Awesome. It's going to form the pyramid shape. So write that down and then we have to sketch it. So you're going to write trigonal, or you can write pyramidal. You can just write pyramidal. Trigonal pyramidal. And it's going to look like this. SB, BR coming down, BR coming down, and BR diagonal coming down. Okay, not in the middle. That would be planar equilateral triangle. And the last thing, we know these are polar bonds. Okay, so we can have polar or nonpolar molecule. Are there dots in the central atom? Yeah. Yes. What does that make it? A polar molecule. Okay. All right, and that's basically it for doing